Alright, hi and welcome. So in this video, I'm going to go through some notes about exponential functions. If you want to follow along with me, you can go through the copy of the notes that I have available. I have like a blank copy that you can write on, or I'll also upload my version that's filled in once we're done. So you can engage in whatever way feels best for you. So starting with exponential functions, we're just going to do the general definition. So we say that the general or basic form of an exponential this is an exponential function, will be written as the following. So it's going to look like f of x equals, and then we have a c times a to the x power. So different people might use different letters for these things. These are just the letters I tend to use. And let's go ahead and label these. So the c value, that's going to be our vertical intercept. And then the a value, that's our growth factor. So we'll learn more about why these words are called what they are, but these are the terms that we have in our exponential function. So we have a vertical intercept and the growth factor, and here we just assume that the values of c and a are positive. So where c and a are some positive values. All right, so what I think of when I think of exponential function is this word exponent. So the exponent, which is part of exponential, and that's why the exponential function is called exponential, is because we now have the variable in the exponent. So rather than having it linearly or part of a polynomial or a rational function, now that variable is in the exponent, and that's why it's called an exponential function. All right. So as we're learning about exponential functions, I just like to do a little bit of a review about how exponents work so that you at least have some reminders about exponentials, well, at least exponents and how they simplify and such. So let's just go through that really quick. So if we have a to the negative x power, so anytime you have a negative exponent, you can rewrite this as 1 over a to the x. So you bring the term into the denominator, into the bottom of the fraction, and then the exponent becomes positive. So you can go between these two anytime you need. Also, if you have two terms multiplied together with the same base, so a is the same base and they have different exponents, you can combine them by adding the exponents. So let me write you like a specific version for each of these. So a to the negative 2, you could write that as 1 over a squared. If you had a to the 3 times a to the 4, this would be a to the 3 plus 4, which is a to the 7th, so you just add those exponents. Then if we have dividing, we have a to the x divided by a to the y. This is the same as doing a subtraction, and that's because you can rewrite that a to the y as a to the negative y using our first rule. So we're subtracting those exponents. This would be maybe like a to the 7 over a to the 5th. This is a to the 7 minus 5, which is just a squared. You can also think of these things as sort of canceling. So like 5 of the a's cancel with 7 of the a's, and we're just left with 2. And then lastly, if we have two exponents multiplied together, we can basically switch the order. So if we have a to the x times y, this is the same as a to the x raised to the y power, or a to the y raised to the x power. So maybe like a to the 6th raised to the 8th is the same as doing a to the 8th and then to the 6th, or this is just the same as multiplying these exponents. So 6 times 8 is 48, so this is just a to the 48. All right, so these are just some rules about exponential functions if you need reminder. And I guess I shouldn't say exponential functions. These are just like rules about when we work with exponents, what happens. So you maybe have done this with like x squared, x cubed, having x as the base. And now we're just looking at having a number a as the base. So these are your reminders from exponent rules. You probably have seen these before. Okay, so we're going to go through an example where we compare these two different functions. So we have two different exponential functions here. And yeah, so we're going to go through the table and then graph them. So let's go ahead and do that. I do have one more note I want to make about a specific base, but I'll do that after this. So we're going to start with these examples. So here I have k as my first function. We have 1/2 times 2 to the x. So here the 1/2 is c, and then the 2 is a. Then we also have j, and j just has those numbers swapped. So the c value here is 2, and then the a value is 1/2. Okay, so we're just going to look at these tables and substitute some things in just to see how these functions behave. So let's go ahead and start with k. So I'm going to plug in -2. That's our first value. We're just going to go like down the list of x's and plug them into our function. So first I have -2. I have 1/2 times 2 to the -2. When we have negative exponents, we can rewrite this as having a positive exponent in the denominator. So I'm going to have 1/2 squared. And then this is like 1/2 times 1/4. So this is 1/8. Okay, so 2 to the -2 is 1/2 squared, which is 1/4. And then we multiply that by 1/2 to get 1/8. Let's try this again with -1. So the negative exponent makes us put the number in the denominator with a positive exponent. And then this is 1/2 times 1/2, which is 1/4. Okay, now we do to the 0 power. So I didn't mention this as my rules, but anything to the 0 power is always 1. I can show a bit of a proof for it. It's not like super interesting. I guess the thing to remember is just that this is sort of our trivial option, and we've decided that it's equal to 1. So when we have a number raised to the power of 0, this is 1. And so I'm getting 1/2 times 1, which is just 1/2. And then we go through the next couple. So these ones should hopefully be easier. So I have 2 to the 1 power. My 2's are just going to cancel, and I'm getting 1. So 1/2 times 2 is 1. Then I do 1/2 times 2 squared. So 1/2 times 4, which is just 2. And then I have 1/2 times 2 cubed. So something just went crazy with my Zoom. So it's doing it again. I'm just going to scroll up a little bit. I think that'll help. Maybe not. Okay. So 2 cubed is 8. 1/2 times 8. Then we do 8 divided by 2, which is 4. So we have our values here. We have our outputs at least. We have 1/8. Oh, and my highlighter's not working. We have 1/8, 1/4, 1/2, 1, 2, and 4. So I'm going to go ahead and plot those. So I have, let's get a little bit of a bigger point here. Maybe blue, I guess. Okay. -2, 1/8. So that's really small. Oh, that was huge. That's not going to work. Wow, I am struggling. So -2, 1/8, something small. Then we have -1, 1/4, a little bit bigger. Sure. Try not to be too much of a perfectionist right now. Then we have 0, 1/2, 1, 1, 2, 2, and 3. Oh, wait. Yep, 3, 4. Okay. I kind of want to do 4. If we plug 4 in, we should get 8. I'm just going to plot that one. You can check that for me. Okay, and so here is our function. It's kind of like this shape that is sort of flat on the left-hand side, and then it gets steeper as it goes to the right. So this is our exponential function, and you'll notice that if we look where the vertical intercept is, this vertical intercept is at 0, 1/2. That was our vertical intercept. which should line up with how we defined everything at the beginning. So we said that the c value was the vertical intercept, and that's working because when we put 0 in for x, we get a 1, and so we're just getting that c value left over. So that c is the vertical intercept, 1/2, and we should see the same thing happen for the other function. Okay, let's go through that now. Let's do this other function. So now we have 1/2 as the base. So I do 2 times 1/2 to the -2. This one's a little bit more work. Honestly, you could just type this in a calculator. I know that what I'm going to do is just write 2, so I'm going to write 1/2 as 2 to the -1. So 1/2 is 2 to the -1, and then I still have that -2 power. So this is a 2 times 2 squared. So I'm putting together these two negatives to get a +2, and so this is just 8. So we have -2, 8. And again, you can always use a calculator if you're unsure about any of these. Okay, now I have -1. So again, I'm going to rewrite 1/2 as 2 to the -1. Then when I multiply those two negatives together, I'm just getting 2 times 2, which is 4. And honestly, we should see a bit of a pattern, so like I'm getting numbers that to me make sense in the pattern. Okay, now we do 2 times 1/2 to the 0. Anything to the 0 power is 1, and so I'm just getting 2 out. That's my vertical intercept that we commented on. So because we put 0 in for the x, we're getting just that c value out. So that's our vertical intercept. All right, now I do to the 1 power. That's 2 times 1/2, which is 1. Then I do squared, 2 times 1/2 squared. That's 2 times 1/4, which is 1/2. And then I do 2 times 1/2 cubed. 1/2 cubed is 1/8. And so I'm getting 2/8, which is 1/4. So I'm going through this, trying not to take too long just so we can get through it. And now let's go ahead and graph these. So, oops. All right, so I have -2, 8. -2, 8. Then I have -1, 4. 0, 2. 1, 1. 2, 1/2. And 3, 1/4. And we'd also get 4, 1/8 if we also wanted to do that. So we're seeing that these are very similar graphs sort of in shape. We actually had a lot of the same points. They just happened in different orders. So this one's steep on the left-hand side and then it flattens out on the right. So we're going to come up with words, or we're going to have words, I guess. We're not going to make them up to describe these behaviors. So when we move from left to right and our values get like more positive, so we're going up, that's going to be growth. So exponential growth. And I'll define that in a moment, but that's just the sort of thing I want to point out with the graph. And then on the second graph, when we move from left to right and we go downhill, that is decay. So increasing is growth, decreasing is decay. Okay, so let me write that out more formally. Yeah, and I guess maybe I can circle the vertical intercept here too. The vertical intercept here was 0, 2. That 2 value was from our c. Okay, all right, let me write some conclusions. So, before we do that, let me look at these really quick. So we had a growth and a decay, and we want to talk about what's different between these. So the growth function had a growth factor, this a value of 2. So 2 was kind of a big number, and as we increased our values, we were like multiplying it more and more times, and so we were growing. Versus on the second function, we had a 1/2 as our a value, and so things are getting smaller over time because we're multiplying 1/2 by itself. So the main difference here was this 2 versus the 1/2. The 2 corresponded to growth as our growth factor. That's the number that has the x on it. So that was our growth formula, or our growth graph, sorry. And then the 1/2 with the exponent was our decay. So we're going to generalize that to some statements. Okay. So if our a value, that's what we're calling our growth factor, if that's greater than 1, Then we have exponential growth. So whatever that a value is, that's our growth factor. If it's bigger than 1, then we have exponential growth. And then if it's less than 1, then we're going to have exponential decay. So I'm not going to write it here, but if we have it equal to 1, that's actually not very interesting because it's just 1 to some power. And anything we raise with 1, so like 1 to any power is always 1. So it's really boring. So we really actually just care about if a is greater than 1 and if a is less than 1. And then just a note, we're assuming a is positive. So we're assuming a is greater than or equal to 0. And honestly, it's probably just greater than 0. So we're assuming that we have a positive a value. And so these are our two cases. So we're going to do some practice where we look at the exponential and determine if it's decay or growth. I also want to mention here before we move on a special type of a value. So if we have a as being equal to e, this is a special thing. So let me write this out. So we say the natural exponential function this is the most standard version of it, is going to look like, oh, I'm sorry, it is f of x equals e to the x. And this e value is Euler's number. So you've probably seen this in a math class before. I guess it's possible maybe you haven't. That's totally okay. If you haven't seen it before, it might be nice to look up Euler's number and just so you can learn a little bit more about it. It's a really special number in math that has a lot of really interesting behavior and properties. So we tend to want to talk about it when we're talking about exponentials or about all sorts of other things in math. And here, just as a comment, this has an a value of e, so of our Euler's number. And then this particular version I wrote has a c value of 1. That's the vertical intercept. That's because there's a 1 in front. So that's just something to note. I'm not going to leave that there, but just in case you were trying to match that up. Okay, so now I just want to make sure we really feel good about the conclusions we made with the growth factors. So I'm going to go to Desmos and just give it some information. All right, so we have c, and then we're going to do times a to the x power. And I'll add those sliders so we can see what's happening. Here we have an a value of 0, which is pretty boring. It doesn't really know what to do with that. It's just like a line, right? I mean, it knows what to do with that, but it's just not very interesting. So I'm going to set up our sliders so that we have at least something between 0 and, I don't know, we could even say 10 as our a. And we want to look at what happens as we get more interesting a values. So as our a value increases, you can see that it gets kind of steeper and steeper. And then it gets interesting when we get less than 1. So as we get less than 1, the graph sort of changes shape. So I'll just go through that manually. If we're on between 0 and 1 for our a value, we're kind of switching between, well, if it's less than 1, it's decay. So you can see the shape is always decreasing of the graph. But then as we get greater than 1, it switches direction. And so now we're doing an increasing graph over time, which is growth. So that is sort of the movement there. And then with the c value, this is the vertical intercept. So as this moves, you should see the whole graph kind of shift up. It honestly looks a little bit like it's stretching or something. And yeah, I guess the negative value makes it go down, but we usually don't think about that. We just think of the c value as moving the graph up or down. And it might be interesting to kind of look at it from further away. You can see the graph moving up and down. The other thing I just want to mention is that this graph has a horizontal asymptote. So as we go to the left here, you can see the values are approaching 0. Or if we have a decay graph, they're still approaching 0 now just on the right. So we have a horizontal asymptote. This also has a domain of all real numbers, so we can input any value for x. But the range is from 0 to infinity, not including 0. So there's no value that gets us 0 as an output, but the rest of them greater than 0 are outputs. So yeah, I think that's what I want to say about the graph, just kind of to show you the vertical intercept as the C, and then show you the decay and the growth with the A. All right, so I'll maybe write a little bit in here for my formal notes just to say what I just said. The domain is all real numbers, the range is from 0 to infinity, and there's a horizontal asymptote at y equals 0. But for now, let's move on. So I just want to go through some examples for the rest of this. So we have an example where we identify growth or decay. We're going to do an example where we match a function to its graph. And we're going to do an example where we find a formula for an exponential function. So these are our 3 examples we're going to end our discussion of exponential functions with. So, okay, I really did not prepare this part, and we are going to need a calculator. So I'll probably do that on the fly, which might be kind of fun. I will take out my phone and do this on my phone, see how that goes. It might involve me finding my phone, and then this way you can hopefully do it along with me. So what we want to do here is identify each of the following functions as either exponential growth or exponential decay. And we're going to do that by finding the a value. So the a value, remember, is the base of our exponential or our growth factor. So honestly, I can kind of just look at these and start seeing what the a is going to be. So I could do like a quick circle of them. So I see like the base, the base, the base. I'm basically just picking all of the parts that are like where the exponent is attached to. And we have a couple of these last 2 have negative exponents, so I'm going to talk to us about how to handle that. But the idea is we're just going to identify that growth factor. So I'll do this a little more carefully than that. I just want to show you sort of what we are looking at. Okay, so on this first function, we're looking for the a value. Remember, our formula is c times a to the x, and we're looking for a. And we have some here that are also to the t power. Okay, so on this first part, part A, I'm seeing that my a value is 1.05. So I have my c is 2/7, my a is 1.05, and then it's raised to the power of x. So growth is if we have an a value greater than 1. Decay is if we have an a value less than 1. Oops, and I said 1, but I wrote 0. That's funny. So less than 1, greater than 1, and less than 1. So 1.05 is greater than 1, and so we're going to have growth for that exponential. That's because we have a value greater than 1. Okay, for this next part, for part B, I'm seeing that our e to the 0.05, 0.05, that is our a value. So it's like 32 is c, and then e to the 0.05 is e. And just looking at that, I'm not really sure if that's like greater than or less than 1, so I'm going to need to use a calculator to do so. I'm just going to use my phone calculator to do this really quick. And hopefully I'm doing this correctly. I'm getting approximately 1.05, which is the same as part A, so this is still growth. So our a value is greater than 1, it's just a little bit greater than 1, and so we have a growth exponential, or exponential growth, I guess. Okay, then on this next equation, we're doing part C now. I'm seeing that there's a 1 in front as my vertical intercept, and so then this 3/4 is my a value. So my a value is 3/4. 3/4 is 0.75, which is less than 1, or you can just think it's less than 4/4. So this is decay, because now we're in this less than 1 category. All right. So we just keep doing this, we just keep identifying a. On this next function, I'm seeing we have 3.4 as the c, and then I have e to the -5 as my a value. So e to the -5. And I'm doing that because I see the t is like attached to it, but I want like a positive exponent. I don't want to do like negative t. I just want to think about t as the exponent, and so e to the -5 is my a value. And then I'll need to determine what this is. You can think of it as 1 over e to the 5th if that's easier. So I'm thinking this is going to be less than 1 since we're taking 1 and dividing it by some big number. But I'll try to get us a decimal just to be sure. So if I have -5, let's see if I can do this on my calculator, and I do e to that power. Yeah, I'm getting a really small number. I'm getting like Oh wait, and I'm gonna rewrite this. Okay. I'm getting 0.0067. So I think I did that right. E to the 5th power. Let me try it one more time. Yep, okay. Did it right. So yep, that's a really small number. That's definitely decay. That's between 0 and 1. Okay, then lastly, we have this 8 times 12 to the negative t. This one's a little tricky. I'm actually going to rewrite it as 8 times 12 to the negative 1 power. And then I have a positive t on the outside. So it's like 12 to the negative 1 times t. And so that 12 to the negative 1 is my a value. So that's like 1/12. That 1/12 is definitely less than 1. So that is decay. All right, so that's what we do for these problems. We just identify the a value and making sure that the exponent is just a single variable. So you don't want like a negative x, you don't want like 0.5x, you want to like get everything together with the a, so it's really c times a to the variable. Okay, let's match some exponential functions to their graphs. So what I like to do is remember that the c value is the vertical intercept. So this is often enough to determine which graph is which. So when I have 1/2 on my function f, that means I have a vertical intercept of 1/2. So I can already find that on the middle graph, and so I'm pretty confident that my middle graph is f of x. And that's because it has that vertical intercept of 1/2. I also noticed the a value is 4. 4 is bigger than 1, and so this is growth, which is good. So this is growth like we would expect it to be, exponential growth. All right, let's look at G next. So I can do a very similar thing. I see that 3 is the C value. That C value is the vertical intercept. So I'm looking for the graph that has 3 as the vertical intercept, which looks like it's the leftmost one. So that's enough for me to be able to tell. Another check you can do is that 2/5 is less than 1. So we're expecting decay if I look at the a value. So this is decay as we would expect. All right, then hopefully our last graph is the right one. So here I have e to the 0.5x. There's kind of like a hiding 1 in front. So I'm looking for that 1 as my vertical intercept. If there's not a value multiplied, you need, like, everything's got a 1 there. We just don't always write it. Like 1 times something is always itself. And then e to the 0.5, we could determine that, but it should be greater than 1 since it's e to some power. And it's not negative. The exponent's not negative. And so this is growth like we would expect. So my suggestion is just to use that vertical intercept. And then if you have two graphs that have the same vertical intercept, try to look at the growth factor and determine if it's exponential growth or decay. And then also you could always substitute in some points. So you could substitute in 1 for x, for example, in all of these, and then see what the output is and then match it to the graph. All right, so we're almost there. Our last example is just to find a formula for an exponential function. So I'm going to walk through this process. It's really not too bad. This time we just have a c and an a value we need to find. And so when we've done some other functions in the past, there's been different ways to get these. And so we're kind of following a similar process here. We just need to find c and a. So what I like to just remind myself of is that c is the vertical intercept. And a is the growth factor. And in a lot of these problems, the setup actually gives you the c value. So it actually gives you the vertical intercept, like it gives you the starting value if this is an application, or it just gives you it as one of the points. So if we look, our 2 points that we're trying to find an exponential function through are 0, 3, and 2, 48. So 0, 3 is actually the vertical intercept. Since if we had a plot, it'd be over 0, up 3. So that gives me my c value. My c value is 3. But okay, I know that because I've done a lot of these. I could be like, oh, that's the vertical intercept, that's c. Let's suppose you like really didn't notice that, or like you're just doing this for the first time. Something you can do is just substitute in each of these points. So we're going to substitute in 0, 3 and substitute in 2, 48. So starting with 0, 3, I'm going to substitute in 0 for x. I'm getting c times a to the 0, and that needs to be equal to 3 as the output. So we'll do the same thing for the other point. I'll just set it up really quickly so that we have it ready. I substitute in 2c times a squared, and that needs to be equal to 48. So here we have two equations and we have two variables we don't know. We don't know the c and we don't know the a. So to do this, I'm going to start with the to the 0 power because that 0 power is always equal to 1. So a to the 0 is 1, and just to write us a little note, a to the 0 is always equal to 1. So this can be really helpful as you're doing these. You don't even need to know what a is. Any number to the 0 power is 1. Okay, so now we have c times 1 equals 3. And this gives me that my c value is 3, like we thought. So this is another way to just always get the c value, is if you have this 0.0 something, you can just substitute it in. So what we're going to do is then take that 3 and plug it into our second equation. So my c value is 3. So I'm going to rewrite this as 3a squared equals 48. So our goal is to find c and a. To write our formula, we have c, we now need a. I find a by substituting in my c value. All right, so let's solve for a here. I'm going to just divide both sides by 3. I am totally having a moment where I'm worried I don't know what 48 divided by 3 is. And I should know because I set this up. Okay, yeah, it's 16. Everything's okay, folks. So I'm getting a squared is equal to 16. And then I take the square root to get my value. So a is the square root of 16, which is 4. And we're assuming a is a positive value, so we don't need to worry about the plus or minus square root. We're just taking the positive version. So that's why I'm doing that here. Okay, so I found my a value by substituting in c, and now we can write my final answer. So my function is equal to c times a, so 3 times 4 to the x. And that is my final answer for my equation. Okay, all right, so that is everything we have for doing exponential functions. We are able to write a formula by substituting in both points and then finding c and a. We were able to match up graphs by looking at the vertical intercepts and then also checking for growth or decay. We were able to determine if an exponential function is experiencing growth or decay by looking at the a value. And to do that, I actually used a calculator to find the decimal approximation of a so that I could tell if it was greater than or less than 1. Then we looked at some graphs on Desmos. We also talked about the natural exponential function, which is a special case with Euler's number e that has a special button on our calculator. We confirmed that if a is greater than 1, we have growth, and if it's less than 1, we have decay. And we practiced graphing a couple exponential functions, went over some exponent rules, and we did the general formula. So okay, that's it. Thanks so much for watching, and I will talk to you in the next one.